This video is education purpose only. Myself, Dr. Jagdale. Today I am going to talk about the Sidgwick model. This topic is belong to the coordination chemistry, T.Y.B.Sc inorganic chemistry, paper number 332. Introduction to Sidgwick model. In 1927, scientist Sidgwick explained the formation of coordination compounds on the basis of electronic theory of valency. He explained the formation of coordination compounds on the basis of electronic theory of valency. You know that valency means number of unpaired electrons present in the valence shell or electrons required for the bonding. He proposed that when there is a formation of coordination compound, coordinate bond is formed, and for the formation of coordinate bond, there are two conditions. First condition is ligands donate lone pair of electrons to the central metal atom or ion, and there is a formation of coordinate bond. In ligand, at least one electron pair is present. Example is suppose NH3 ligand. In NH3 ligand on nitrogen, you know that there is one lone pair of electron. That lone pair of electron is donated to the central metal atom or ion and coordinate bond is formed. Second example is water molecule. You know that water molecule is English V shape, and on oxygen there are two lone pair of electrons. And according to the Sidgwick model or Sidgwick theory, electrons are donated by ligands and each ligand contains at least one lone pair of electron. Second condition for the formation of coordinate bond according to the Sidgwick model is that when there is a donation of electron pair from ligand, that donation is partial and not fully. When there is a partial donation of electron from ligand to the central metal atom, coordinate bond is formed and that bond is shown by arrow. That bond is shown by arrow. Example is suppose there is a formation of here Cu, then NH3 2 plus complex ion. In this complex ion, Cu is central metal ion and 4 NH3 ligands are directly attached to this Cu2 plus ion. The structure of this complex compound is represented as at the center position there is copper, then 4 NH3 ligands are surrounded by that Cu, and here is NH3, here is NH3, then NH3 and NH3. Then charge on this complex ion is 2 plus. 4 coordinate bonds are formed. These bonds are shown by arrow. The reason is that on nitrogen means every nitrogen in NH3 ligand, one lone pair of electron is there, and that is the introduction for this Sidgwick model. That is introduction for Sidgwick model means each ligand contain at least one lone pair of electron, and that lone pair of electron is donated partially to the central metal atom or ion, and there is a formation of coordinate bond. That bond is shown by arrow. That is the introductory part for the Sidgwick model. Second, what is effective atomic number rule? It is represented as EAN rule. It is represented as EAN rule. According to the Sidgwick model, when coordination compound is formed, it obeys the effective atomic number rule. What is effective atomic number rule? When coordination compound is formed, the central metal atom or ion try to acquire the nearest zero group or inert gas electron configuration. Example is, suppose there is a formation of Fe here CN6 4 minus complex ion, and according to the EAN rule, EAN is equal to here A minus B plus C, where A is atomic number of central metal atom or ion, then B is charge on metal ion, and C is number of electrons donated by ligands. In this complex compound, here central metal ion is iron, then charge on that iron is 2 plus. Why it is 2 plus? Here for every cyanide there is minus 1, 6 cyanide ligands are, here is minus 6, and you know that charge on complex ion is determined by algebraic sum of all charges. Algebraic sum means here 2 or plus 2 minus 6 is equal to minus 4. Here plus 2 minus 6 is equal to minus 4. Here A is equal to atomic number of central metal, and you know atomic number of iron is equal to 26. Then charge on iron, that is equal to minus B minus 2. Then here plus C is number of electrons donated by ligand. You know that every ligand donates 2 electrons. Here 2 multiply by 6 cyanide ligands are there. Here 6. That total is equal to 26 minus 2 plus 12, that is equal to 24 plus 12 is equal to 36, and 36 is nearest inert gas configuration, that is a zero group element krypton. Krypton has atomic number 36. You know the zero group elements: helium, neon, argon, krypton, xenon and radon. Helium has atomic number 2, then neon has atomic number 10, then argon has atomic number 18, then krypton has atomic number 36, xenon has atomic number 54, and radon has atomic number 86. Here 36 is the atomic number of krypton, and it is the nearest zero group element for iron. Iron belong to the, you know that D block, means transition metal series, first series. First series elements are scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and zinc. Their atomic numbers are from 21 to the 30, and these 10 elements are included in first series, and iron belong to the first series. Atomic number is equal to 26, and this is the example for effective atomic number. Listen again. Effective atomic number rule is that the metal ion in coordination compound try to acquire the nearest zero group electronic configuration. How it acquire? That effective atomic number is equal to A minus B plus C, where A is atomic number, B is equal to charge on the metal ion, and C is the number of electrons donated by ligand. For this example, FeCN6 4 minus, here An is equal to 36, that is equal to krypton electron configuration, means for FeCN6 4 minus complex ion, it obeys the Sidgwick effective atomic number rule. Second example for the formation of Sidgwick effective atomic number rule is neutral complex compound. Example second is neutral complex compound is NiCO4 complex. This is a neutral complex. This is the carbonyl of nickel, known as nickel carbonyl NiCO4. In this nickel carbonyl, here effective atomic number rule, EAN is equal to A minus B plus C. You know that A is atomic number atomic number of nickel is equal to 28. Then charge on nickel is equal to 0 because carbonyl is a neutral ligand. Charge on carbonyl is 0. 4 carbonyls are there, but here charge is equal to 0. Therefore, charge on complex ion is 0. Means B is equal to 0. And C is equal to number of electrons donated by ligands. Here 4 ligands are there. Each donate 2 electron. 2 multiplied by 4, that is equal to 28 plus 8, that is equal to 36, and 36 is again krypton electron configuration. Means NiCO4 neutral complex obey the effective atomic number rule, and that En is equal to 36. It is equal to the nearest inert gas configuration krypton. Next example, third example, for the effective atomic number rule is here Fe, then CO5. In FeCO5, effective atomic number rule En is equal to A minus B plus C. You know that the atomic number of iron is equal to 26. Charge on iron is equal to 0. Here minus 0 plus 5 carbonyl ligands donate. Each donate 2 electrons. 5 2s are 10. Here 10, and total is equal to 36. 36 is krypton electronic configuration. Therefore, all these 3 complex compounds obey the effective atomic number rule. And what is effective atomic number rule? ENA is equal to A minus B plus C. Means central metal atom or ion try to acquire the nearest 0 group electron configuration. But there are number of compounds they does not obey the effective atomic number rule. Example is, suppose there is a formation of FeCN6, here 3 minus complex ion. When FeCN6 3 minus complex ion is formed, the charge on complex ion is equal to 3 minus. Charge on complex ion is 3 minus. Then again, here effective atomic number rule EAN is equal to here E minus B plus C. Here E is atomic number of iron, that is equal to 26. Then B is equal to here charge on iron, that is 3 plus why? Minus 1 on every cyanide, here minus 6. And charge on complex ion is determined or calculated by algebraic sum. Here plus 3 minus 6 is equal to 3 minus. Plus 3 minus 6 is equal to 3 minus. Therefore, charge on iron is equal to here minus 3 and plus here each ligand donate 2 electrons. Total 6 ligands are there. Here multiply by 6. Here 26 minus 3 plus 12, therefore 23 plus 12 is equal to 35, and 35 is not electronic configuration of nearest 0 group element as krypton. Means FeCN6 3 minus complex ion does not obey the effective atomic number rule. The next example means second example that does not obey the effective atomic number rule is, suppose there is a formation of Cr, then NS36 3 plus complex ion. There is a formation of Cr NS36 3 plus complex ion. In this complex ion, here effective atomic number rule is equal to A minus B plus C, where A is equal to atomic number of chromium is equal to 24. Atomic number of chromium is equal to 24. Then charge on chromium is equal to plus 3 because this is a neutral ligand. NS3 is a neutral ligand. 6 NS3 neutral ligands are there. Therefore, charges is equal to 0 and algebraic sum is equal to plus 3 plus 0, that is equal to 3 plus. Therefore, here B is equal to minus 3. and 6 ligands are there, each donate 2 electrons, and total is equal to 24 minus 3 plus 12, that is equal to 21 plus 12 equal to 33, and 33 is not equal to the krypton electron configuration, and these two complex ions does not obey the effective atomic number rule. Means there are number of complex compounds, they are obeying the effective atomic number rule and not obeying the effective atomic number rule. These two are the examples for coordination compounds having not obeying the what effective atomic number rule. Means in number of cases that Sidgwick model get fails. Then what are the applications, means advantages of Sidgwick model? Next point is applications or uses of Sidgwick model. First application for Sidgwick model is, this model simply explains the formation of coordination compound and coordinate bond in number of complexes. Means electronic arrangement in coordination compounds is explained by the Sidgwick model. Second application for this complex compound is, here Sidgwick model explains how coordinate bond is formed and the stability of coordination bond. Indirectly, it explains the stability of coordination compound. Means first application, this theory is a simple theory for the explanation of electronic arrangement in coordination compounds. Second, it gives the stability of coordination compounds. You know that here organometallic complexes like NiCO4, then Fe, here CO5, then there is a formation of COC6, then S6, twice type of coordination compounds, and their stability is explained by the Sidgwick model. Also, third application for Sidgwick model is that there is a formation of coordinate bond. This bond is shown by arrow. This bond is formed due to the partial donation of electron and the formation of NH4 plus ion, ammonium ion. And how coordinate bond is formed there, it is explained by Sidgwick model, and these three are the applications of Sidgwick model. Then next point is, what are the limitations or disadvantages of Sidgwick model? As compared to the advantages or applications of Sidgwick model, number of limitations are more, and that's why Sidgwick theory get failed to the what? Formation of coordination bond. And next point is limitations of Sidgwick theory or Sidgwick model. First limitation is that this model explains only the formation of coordination compound in transition metals. You know that transition metals means D block elements. Transition metals, D block elements, and it get fails to the formation of coordination compound, means effective atomic number rule for other metals like alkali metals, alkaline earth metals, then some F block elements and some P block metals. Then second limitation for Sidgwick model is, once there is a formation of coordination bond, according to the Sidgwick model, there is a donation of electron and that compounds are more stable. Actually, when donation of electron pair is occur from ligand to the metal ion, there is a decrease in stability of complex compound. There is decrease in stability of complex compound. Third one, there is a formation of coordinate bond, and that bond is shown by arrow. But that arrow is not represented in all cases. Example is, suppose there is a formation of this type of compound, here Cu, then NH3,4Cl2. The structure of this complex compound is represented as Cu is at the center position, then 4 NH3 ligands, their bonds are shown by arrow. Because on nitrogen, lone pair of electrons are present, then 2 chlorides are here. These 2 chlorides are not shown by what? Arrow. This bond is covalent coordinate bond. This bond is coordinate bond, and for the representation of such type of complex compound, means CuNH3,4Cl2, Sidgwick model get fail. Then next limitation of Sidgwick model is number 4. It cannot explain or not explain the geometry of the complex. You know, the geometry of complex is important. It gives the shape or structure of that molecule, and again the arrangement of electrons. But geometry of complex is not represented by Sidgwick model, and that is the limitation of Sidgwick model. Fifth limitation for Sidgwick model is that according to the Sidgwick model, there is a donation of electron pair from the ligands. Example is, suppose there is the NH3 ligand, and in NH3 on nitrogen there is a lone pair of electron. In this complex compound, coordinate bond take place from the nitrogen, means donation of electron occurs from the nitrogen, and nitrogen has atomic number 7, and ground state electronic configuration is 1s2 2s2 2p3. Here 3 unpaired electrons are present in 3p orbitals, means px, py and pz, and lone pair of electron is present in 2s orbital, and actually this 2s orbital does not take part in the bonding. Second example is, suppose water molecule is formed, that is H2, and you know that in water molecule on oxygen there are 2 lone pair of electrons. Here oxygen has atomic number 8, and ground state electronic configuration is 1s2 2s2 2p4. Here in p orbital 4 electrons are there, and in 2s orbital 2 electrons are there. Here 2s orbital is completely filled in NH3 ligand in nitrogen, in H2 ligand in oxygen, and therefore it does not take part in the bonding, and all these are the limitations of Sidgwick model. Means there are few advantages or applications of Sidgwick model, but number of limitations are more, and number of coordination compounds are formed even though they are stable but does not obey the what? Sidgwick model effective atomic number rule. Means there are so many complexes, that is limitation number 6, they are not obeying the effective atomic number rule, but they are even stable for the formation of what? Metal ligand bonding, and all these are the limitations and applications of Sidgwick model, and this is the Sidgwick theory for the formation of coordination bond, effective atomic number rule, compounds obeying the effective atomic number rule, compounds not obeying the effective atomic number rule, then applications of Sidgwick model and limitations of Sidgwick model, and as compared to the applications, number of limitations are more. Therefore, Sidgwick model get failed to explain the formation of electronic structure, coordinate bond, even though there is no study of spectroscopic analysis and geometry of the coordination compound, and these are the limitations of Sidgwick model, and that is the end of Sidgwick model. I hope it is enough to the what Sidgwick model. Okay, thank you.